unit 5, this is talking about rational exponent and radical function. So first thing first, right? So when we think about rational exponent, we understand exponent. Exponent makes sense. But rational exponent, rational means fractions, right? Rational number means something can be expressed as a fraction. So when we talk about exponents are written in fraction form. Okay? So that's really the key idea of this chapter, is that we're dealing with stuff that has to do with exponents, but exponents that may not be as typical as what we are used to see. They are all mostly in fractional form. And then radical function, it has to do with functions that are, that has exponents are the rational exponents, or that they're radical functions. So square root of x, f of x equals square root of x, or f of x equals the cube root of x, f of x equals the square root of x plus 1, things like that. And how do you then graph those functions, right? So this is a big picture. Got it? So now, phi 1, we're setting up a stage and look at a little bit of review, brief review on exponents and radical. Okay, so first thing first, I'm just going to go down this process. 2 to the third power, that's pretty simple. We know this is 2 times 2 times 2. In fact, we know that this is 2 to the 1 power times 2 to the 1 power times 2 to the 1 power. And so if that's the case, 1, 1, 1, and these are multiplying, and they all have the same base, somehow we want to draw a connection between the 1, 1, 1 here with 3. Seems to me that we can think of this as 1 plus 1 plus 1, so it's 2 to the third power. Now let's test this theory and see if that works, right? So if you have 2 to the third power times 2 to 2 squared, 2 to the third power 2 squared, this in a sense is 2 times 2 times 2, right? 2 to the 1 power, 2 to the 1 power, 2 to the 1 power. So that is the 2 to the third power. Multiply by 2 times 2, or 2 to the 1 power, 2 to the 1 power. This is 2 squared. So when you multiply this out, you end up with 2 to the 5th power. Well, if you look at this, just looking at these ones, relative to its relationship with this 5, or 3 and 2 relation of 5, you can think of this as 2 to the 3 plus 2, which is 2 to the 5th power, right? So in a sense, right, and then you can reverse, you can do it all these different ways. So in essence, what we can draw a conclusion, which, with these kind of exploration, one could draw a conclusion that a to the n power times a to the m power is a to the n plus m. Okay? This is the conclusion we draw upon. We probably learned this before, but I think today we're just going to be systematically all put it together in one page so that there's no confusion about it. Sometimes we get confused a little bit with situations like this. Say, for example, 2 to the third power times 3 squared. 3 squared. So let's think about this. Okay, if you have 2 to the third power times 3 squared, you get 2 times 2 times 2. So 2, 1, 1, 1, 1 power. And then times 3 times 3, which is 3, 1, 1, 1. And then you look at this and you say, well, this is still, it is what it is. It's still, there's nothing we can join these two parts of the equation, right? I mean, one could say that this is, 8 times 9, right? Is 8 times 9. And so your final answer doesn't give you any sort of pattern. So there's nothing you can do. So this will remain 2 to the third power times 3 squared. Nothing you can do with the exponent. And we see this, we realize that we can't do anything with the exponent. Why? Well, it's particularly because you have two different bases. What's basis, right? Basis will be a to the n power. This is the exponent, and this is the base. And when you have two different bases, you can't really do anything with the exponents. You can only do something with an exponent. In this case, adding the exponent when you had the same basis, and then there's a multiplication. So take an example of, say, 2 to the third power plus 2 squared. 2 to the third power plus 2 squared. I say that because I see oftentimes students get so confused because, you focus on memorization, right? You memorize rules and algorithms and patterns, and then at some point you forget, and then you didn't think through, so I see people just will go ahead and write this as 2 to the 3 plus 2, which is 2 to the 5th. We know that's not true because 2 to the 5th is this one from before, not this one. So that wouldn't work, right? And how do we know that wouldn't work? Well, we can break it down more, right? Break it down more, right? So this would have been 6 plus 4. Oh no, 8 plus 4, which gives you 12. You see absolutely zero pattern here, right? You can't really do anything with the exponent. So you wouldn't do anything with the exponent. So it's continued to be 2 to the third power plus 2 squared. Nothing you can do about it. Nothing you can do about it. If you have the same basis, different exponents, but it's not a multiplication. If it's not multiplication, there's nothing, literally nothing you can do. Okay? So if I want to write it down completely, right, just be extremely clear. When you have a to the n power plus a to the m power, it is still a to the n power plus a to the m power. Now, you may think this is too obvious to state, but I don't think it's too obvious. People make mistakes anyway, all the time that I see. So I need to make sure that I put on the board that you remember. Questions on this?
So this would just be is equal to 2 to the third plus 2 to the second?
Here? This one? Yeah.
Yeah.
You have a question?
No.
No, okay. All right, now go on to the next one. The next one. We're just gonna keep building this up, okay? We can keep building this up. 2 to the third power divided by 2 squared. 2 to the third power divided by 2 squared. This is 2 times 2 times 2, 1, 1, 1. And then 2 times 2, right? And this one we know, that's pretty easy. If you break it down like that, you can cancel one set of 2, you can cancel out another set of 2, and then your final answer is 2 to the 1 power. Now, if you look at this and you say, oh, what does that mean, right? 3 and 2, somehow they divide. When they're dividing, it seems to me that you can simply take the exponent And then instead of adding, you subtract. Right? When you subtract, taking the exponent, and notice they're the same, right? Same basis. And instead of multiplying, which you add exponents, you are dividing, and when you divide, you subtract the exponent. So what that means is we can suggest that a to the n over a to the m could be written as a to the n minus n, right? So that. Okay, next one. You're gonna keep building this up, okay? Keep building this up. 2 to the third power divided by 2 to the third power. Now we know immediately this is equal to 1, right? Equal to 1. Makes sense, right? E of a, 1. But if we break this down, right, you got 2 times 2 times 2, 2 times 2 times 2, right? And then you cancel, right? You cancel. This set gone, this set down, this set gone, and you end up with 1, right? You end up with 1. You end up with 1. Makes sense. But if I want to use this rule that we just come up with, use this rule, it would have been 2 to the power of what minus 1? It would have been what? 3 minus 3, isn't it? Right? Would have been 2 to the power of 3 minus 3. And this would have been 2 to the 0 power. Ha! That's where any power to the 0 power, or anything to the 0 power is equal to 1 come from. Because it comes from here. It comes from taking the exponent, subtract exponent, and end up to be 0. And this turns out to be 1, because we want to be consistent with this 1, right? So if you say this is equal to this equal to this equal to this, that makes sense, right? So what do we have, right? Right? We have a to the 0 power will always equal to 1. Because we know this means a to the m over a to the n. This is what it means. Anything to the 0 power is basically suggesting that you're taking that divided by itself. Okay? Make sense? There was one more.
AM over AM, you said?
M and M, right? M and M, which is a to the 0 power, and a to the 0 power. Anything to the 0 power is equal to 1. Anything to the 0 power equal to 1. And so next time, if I ask you a question on the test and I say, explain to me in your own words why anything to the 0 power is equal to 1. Do you know how to explain it to me? You should, right? You should come up with some examples to show the patterns, like based on those logics. Come up with a thoughtful answer. Okay, so we got this one down, this one down, this one down, this one down. 4 different ideas. Now, I'll continue, right? So I'll keep going forward. Um, 1 over 2 to the third power. Can I write this as, right on the bottom is still 2 to the third power. The top, I want to keep it as 1. Can I write that as 2 to the 0 power?
Yes.
Yes, right? Okay. Now, can I write this as 2 to the 0 minus 3?
No.
No.
Never mind. Never mind.
Right? A to the n power over a to the m power is equal to a to the n minus m. If the n power is 0, m is 3, then I can write 0 minus 3. So can I write it as 2 to the negative 3 power? Okay, so if that's the case, if you have 1 over 2 to the third power, it's equivalent to 2 to the negative 3 power. So what does this mean? What does this mean? That means when you have a to the negative n, it's just equal to 1 over a to the positive n. Okay? So there you go. So now take a look at this. Take a look at this. I go back to this one. I'm using this idea. I come over here. I come over here. I'm going to use this alternative way of solving this exactly the same problem. I'm trying to create some mental malleability in your brain, right? Be able to see things in this malleable process as long as they're connected with logic, right? Can I write this as 2 to the third power times 1 over 2 squared this one is this one. This one is the 1 over that. Yes or no? Yes, right? Makes sense? So far, so good. Can I write this as 2 to the third power times 2 to the negative 2 power?
Yes.
Yes, right? Yes. So can I write this as 2 to the 3 plus negative 2? Because it's multiplying, so you add the exponent. So it's 3 plus negative 2. So you end up with 2 to the 1 power. You still end up with the same thing. But I manipulate it in so many different ways to prove some points. Where some of these rules are all logically connected. Makes sense, right? So you can basically take one problem and you can tackle them in all these different directions. You can think of it, sometimes people like to go in this direction. People like to look at this as this. Like some people really like to do it like this. Some people like to do it, the other way around. So you can solve these problems or look at these numbers and expressions in different ways. Questions so far? All right, next one. 2 to the 1/2. Let me do this one. Square root of 2 times square root of 2. We think of this is the square root of 2 times square root of 2, we end up with what? Come on, stay with me. Square root of 2 times square root of 2 is 2, yeah, okay. And 2 to the 1 power. 2 to 1 power. Now I'm writing 1 here because I want to draw your eye on the exponents, right? If I would say this is 2 to the 1 power, and somehow I got 2 to the some sort of a exponent, and they're multiplying. So that means you gotta have to have 2 to the this plus this to equal to 1. What do you think that blank should look like? What number should go into that box? Huh? 5?
I.
Huh?
I as in
I? 1/2, right? 1/2 plus 1/2 gives you 1, isn't it? So this must be 1/2, right? So somehow, square root of 2 is 2 to the 1/2. So we see here is square root of 2 is 2 to the 1/2. Now, I'm not done yet. I'm going to kind of build on this a little bit more before we come up with the pattern, the general pattern. Right? So, cube root of 2 times cube root of 2. Well, since it's cube root, that means I need to do it 3 times, isn't it? 3 of the cube root of 2 multiply to each other in order to get you 2 to the 1 power. Same idea. 2 to the what power times 2 to the what power times 2 to the what power is going to give you 2 to the 1 power. 1/3, that's right. This has to be 1/3. 1/3. 1/3. In order to get you 2 to the 1/3 plus 1/3 plus 1/3, right? 2 to the 3/3, which is 2 to the 1 power. Okay, so simple rule here, right? Simple rule here is that if you have nth root of a, well, this is a nth root of a, this just means you got a to the 1/nth power. 1/nth power. So if today is a square root, you have a to the 1/2. If you have a fifth root, that means it's a to the 1/5. Okay? I'm moving fast enough to make this happen. All right, next one. 2 squared to the 3rd power. I'm breaking it down really simple, right? 2 squared to the 3rd power. Well, 3rd power means you have that thing 3 times, right? Multiplying. And what's inside is 2 times 2. 2 times 2.
So the wait, so we're using minus 2 to the power of 6 and then go and to which would be 4 times 4 times 4, which would equal to 64.
Yeah, but I'm not interested in the final answer. I'm interested in the pattern. Okay? I'm looking at the pattern. You're right. This is 2 to the 6th power. And when we break it down like this, it is almost like so it's too obvious. But I'm interested in the pattern because when I get to the more complex expression, I need to be able to utilize these patterns. So in this case, right? In this case, 2 to the 6th power, the only way we can get to 6 seems to me you have to take these two numbers, since they're power to power. That means in this case is 2 times 3 to get you 2 to the 6th power. Right? Same thing if you do it in a slightly different form, 2 to the 3rd power squared, and you got two things multiplying to each other. So 2 times 2 times 2, 2 times 2 times 2. This is still going to give you 2 to the 6th power. And in this case, it is 2 to the, right, 3 times 2 is equal to 2 to the 6th power. So what does this mean? This means that if you have the same base, a to the n power to the m power, right, power to power, then you end up with a to the n times m. Now, this is important because we're going to mix them with a radical function. We're going to mix this idea over here with this idea, right? We're going to combine these different things. So, moving on from that and building from that, we get, right? So here we got 2 to the 1/2 power squared. 2 to the 1/2 power squared. Now we know 2 to the 1/2 power just means square root, right? But no, it doesn't matter. We can do it this way. If we use this process, right? If we use this one, this just means is 2 to the 1/2 times 2, right? Which is in this case 2 to the 1/2. Okay, let's see. Let's keep going. 2 to the 1/3 power squared. Then we got 2 to the 1/3 times 2, which is 2 to the 2/3 power. Now, it doesn't really matter what this ends up to be. I mean, eventually, when you're solving problem, you do need to figure out certain values or evaluating values. But what I'm interested in seeing the pattern, right?
This better help you like when you first introduced imaginary numbers were just as like what, but I think I get what you're trying to say here. If I'm correct, didn't we have this before where this would be 2 to the 2nd power cubed?
2 to this. I'm not quite sure what you're referring to, but I do want to go over here to kind of help you think through this. If you look at this, this is simply means is a cube root of 2 squared. If you look at this simply means if you look at the original one, 2 to the 1/2 power is just a square root and then squared. What I want you to notice is this is what I want you to kind of look at, is the exponent relative to the look of this whole thing. Right? If you look at this exponent, you have 2 to the 2/3 power. The 2, the whole number in the numerator, is the power on the outside. The denominator, this 1/3, is the root. Right? So what that means is that again, doing this again, A, right? If you have a M, oh, I'm sorry, here, let me do it this way. If you have A to the N over M power, A to the N over M power, this just means you got M root of A, the whole thing to the N power. Or you can think of this as A to the N power, and then the whole thing M root of that.
Oh, yeah, that's why I was thinking of earlier. That's how I meant.
Yeah. It can look like either one of those. Okay? And this is important, right? So this, because we're going to utilize this, and we're going to need to be familiar with the look, because oftentimes I think students get tripped up on solving problems is because they couldn't translate from one look of the expression to another look in which they may be more familiar with. Right, so that's why I say malleability. You have to be malleable to be able to kind of go in either directions. Questions on this so far? So, examples. Examples. evaluate 27 to the 2/3 power. 27 to the 2/3 power. Well, what I want to do typically, right? I'll just do one. I'll do this one for you to show you sort of some of the kind of the small things I do. So I typically I'll take the base 27. I typically want to pull out the base, and on a separate part, and I say this is what I'm going to do. I'm going to say, okay, what is a number that can divide 27 and give the smallest factor? The smallest factor I can think of is 3, right? So I can think of 3. 3 divided by 27, I get 9. I repeat on the 9 again, and I say, well, what smallest factors I can divide the 9 by? Okay, 3 again, and finally the answer is 3. So that means 27 can be break it down into 3 times 3 times 3. Right? So I'll write it down here. This is 3 to the 3rd power. Okay, so then I go here and I say, instead of writing 27, I'll write 3 to the 3rd power to the 2/3 power. And we just learned from before, right? A to the n times m, a to the n to the m power is equal to a to the n times m. So it's 3 to the 3 times 2/3. Right? 3 times 2/3. And 3 times 2/3 is just 2. So it's 3 squared, which is 9. So 27 to the 2/3 power is 9. Yeah.
Would you have done it? You know how you split the 3s into 3? Well, if you just go to the second 3, but it's
So,
well, when you figured out that there's 3 to the power of 3 is 3 squared and 3, then you already found your answer.
yeah, I'm breaking down to the most detailed form of it. Obviously, you can do this all in your head. What I'm saying is that I'm building on the simplest form so that, like more complicated parenting can reduce the same.
If we get a fraction of this on test, like really complicated, do you want us to break it down? Is that how we find it?
On the test, I'll tell you exactly. On the test, ideally, I don't like to assess you on whether you can do the simple operation. Ideally, what I would want to do is give you a function to tell you what, right? And that function is going to involve small things like this, that, and then where you have to, whereby you have to simplify them and make it into a recognizable function. Does that make sense? And that's how I would typically test you, right? So if I will give you a radical function that has 27x to x plus 1 in parentheses to the 2/3 power and this and that, and then I want you to grab it, and then you will have to utilize these processes, right? So I typically wouldn't give you a simple problem like this, or I wouldn't give you a problem like this with a more complicated number. You will get that in the back of the section in the textbook where they will give you and say, for example, they give you like 75 to the 3/5 power, right? So 75 to the 3/5 power, and then they may say, oh, well, what can you simplify that to the smallest way possible? So in this case, I'll give you another one, right? So you do the similar thing, do the similar way, and just for the practice, 32 to the 3/5 power. Go ahead and simplify this down, right? simplify this down. 32 is pretty big. Now, oftentimes it's justification, so if you can look at this and come up with the answer, or someone would not hesitate to pull out a calculator and start calculating, you can actually come up with the right answer. But I may say, okay, can you show me the process in which this leads to that final answer? I can just tell you what the final answer is. The final answer is 8, right? Final answer is 8. But you got to tell me how you get 8. Well, you justify the process to get 8. The answer is 8. Show me how you get 8. You got it? Here, come show me how you get 8. Yeah, perfect. Yeah, and I bet some of you may have a slightly different process leading up to it. Yeah, so you are 3 and 3. No. This is you should be 5 and 5. We cancel out the 5. This would be 5. 2 to the third power, and then you have 2 to the third power. 2 to the third power is 8. So you may come up with different, right? Some people do it differently. Some people use 32 like y to 30. You broke it down this way. I use this way. I get 16, 8, 4, 2, and 2. So this is 2 to the fifth power. Right? It's the same thing. Exactly the same thing. And then you did this. You did 2 to the fifth to the third, 3/5, and then I would just simply say, oh, that just means 2. Right? Because the 5 and the 1/5 cancel out. So you end up with the 3 right there. It doesn't matter, it leads to the same place, right? And what Leo did is perfectly logical, right? So it doesn't really matter. Okay? Ultimately, it doesn't really matter. What matters is how you justify the solution. So, in the same way, why don't we say, okay, why don't you, actually, let me use the black color here. In the same way, and we're almost done with this lesson. Very, very, very good. Example, right? Say simplify 5th root of 32m to the 15th power. So all of a sudden, you have to utilize all these different things, where all these different little conclusions that we come up with and apply to this. So go ahead and simplify this to the simplest term possible. Now, ultimately, like math is not about simplifying the terms. Math is about recognizing functions and be able to use functions to describe what you want to describe in the mathematical world or physical world. But that expression could look just as complicated as this. So if we can simplify something like this, we can apply it to simplify more complex functions. 32 what?
32 m to the power of 3.
Power of 15. Oh, you mean the final answer?
But it's,
Oh, yeah. 32 answer is 2m to the. I think I have.
yeah, it's 2.
I had 2m to the third power.
I don't know if it's the 32, I think it's.
My answer, I'll give you the answer. The answer is
Well, like, I
2m to the third power. The question is how you get there, right? How you get there.
But
The answer is 2m to the third power. But I want you to be able to figure out how to show me how you get there. I'm more interested in the beginning steps.
I don't realize
So one of the steps. But that 15 only applies to n, not to 2. So this is where m to the 15 over 5. But, so you're saying the fifth root of 32 gives you 2. It's just not. You would, if I'm being just super picky, especially if I deal with problem with just we want to say, if you want to do 32 to the 1/5 and add 15, as an intermediate step, and then you can say this is 2. That works. You got it? How about you guys got it?
well, I thought we met it rather. He says, well, can't really say you root it or you root it, so you five root it, and then you subtract by basically you argue.
Oh, and okay. Yeah, okay. Let's just do it together. So here you have to be careful, okay? This 15 right here only applies to m, doesn't apply to 32, right? So you got to be careful. So what one could do is you can say, oh, this is 32 m to the 15. So these are basically two multiples, and then to the 15 to the 1/5 power, right? You can do that. So then the next step, apologies, this board is awful. so this one can apply to, right? So this is 32 to the power 1. So you can apply to like this. You can apply it out like this. If this is multiply. If you're multiplying, then you can distribute the exponent, right? So Bobby, I should another one here is if you have a times b to the n power, this is a to the n times b to the n power. So this is probably something I need to write down. So make sure that you have that. Okay, like that. So in this case, then you got 32 to the 1/5 power times m to the 15/5, right? 15/5. Now 32, right? 32, we got 2, 16, 2, 8, 2, 4, 2, 2. So this is 2 to the 1, 2, 3, 4, 5 to the 5th power. So I get 2 to the 5th power to the 1/5, right? Times m to the 15/5. Then I get 2, right? 1/5 power times 1/5, so it's just 2 to the 1. And this is m to the 5th power, so it's 2 m to the 3rd power. Okay. Hopefully this is straightforward. Hopefully this is straightforward. Last example on this whole set is find x, right? 2 x to the 5th power is equal to 64. Find x. Without using your calculator, right? The final answer x is equal to 2. X is equal to 2.
Oh, wait, was that? Which one's our next reference? This is.
So do you have the next step is divide by 2 on both sides, so you get x to the 5th power 32. Right, so then x is equal to the 5th root of 32. But we know that 32, right, this is 5th root of 2 to the 5th power, right? I mean, you can think of this as to the 5th power to the 1/5 power, and then so x is equal to, right?
Oh, what I did was I just did that I times everything by 1/5 as well as 64. So
What did you do?
I times everything by 1/5, including 64, and got 4. And
Times or to the power of 1/5?
Yeah.
But then what do you do with this? Did you do something with this?
Then I just divided the 2 afterwards. After getting x, 2x, 2 times x, I just divided the result.
Oh, are you saying that you do 1/5 on this and 1/5 on this? Is that what you're doing? Oh, okay.
And 5.
That works. That works. Yeah. Could be my only feedback is it could be a little bit slightly more complicated because you're gonna deal with 2 to the 1/5 power and so on and so forth. It's a little more complicated. You can get there. You can get there if you're careful. I would say, Joey, in the future, if you have an expression where the exponent doesn't apply to the other parts of the multiple, get rid of those multiple multiple first, right? Or
Oh.
divide 2 on both sides, or you just deal with singular exponent.
Okay, because the way I dealt with that was by separating 2, because I put it's 2 times x to the fifth times 1 fifth.
Right. So if you think of it as 2 times x to the fifth power, then divide both sides by 2 to get rid of this, so isolating x.
Okay,
Right.
got it, because I just did that with multiple, but then did the 1/5 thing, so it wouldn't.
Sure. I'm not gonna say that that's.
I get what you're saying.
Yeah.
Calculate, because it is easy, especially in these stuff, basically 2m to 15 also means like, and 15 goes for each as well as an example.
Yeah, I mean it's multiple pathway, right? Okay. All right. So if you look carefully, section 3.2 is not all that much different than what I just taught you. I mean, if I give you one, just indulge me, I'll do one more example. This actually came straight out of section 5.2. I'm sorry, 5.2. This is 5.1. But section 5.2, say for example, if you had this expression, say for example, find fifth root of 16 times fifth root of 8 in reduced radical form. Reduced radical form. Now, this one immediately you should recognize that. First thing first is this is multiplying. Second thing that you notice is that they're both fifth root. So they're both fifth root, that means 16 to the 1/5 power times 8 to the 1/5 power. Right? But you can't do anything with the 1/5 power. You can't add the exponent because they have two different bases, right? Two different bases. You can't really touch them right now. You can't touch them right now. But then I have an inkling that I can change the 16 and the 8 into the same basis, right? So 16, right? We know 16 to 8 to 4 to 2. 16 is 2 to the 4th power, right? And 8 is 2 to the 3rd power. So I can turn that into 2 to the 4th power to the 1/5 times 2 to the 3rd power to the 1/5. And so I end up with 2 to the 4/5 power times 2 to the 3/5 power. Now I have the same basis, right? Now I have the same basis. That means I can add the exponent. So I end up with 2 to the 4/5 plus 3/5. Well, it's just pretty convenient that they're both, the same denominator. So then this is 2 to the 7/5. 7/5. Now, if this is 2 to the 7/5, right? So wouldn't this just be 2 to the 1/2 power? So that just means 2 times 2 to the 2/5 power, which is 2 times 5/5 root of 2 squared, which is 2 times 5th root of 4. Right, simplest radical or reduced radical. I mean, one could end up right here. One could end up right here by splitting off from here and say, oh, this just means is 5th root of 2 to the 7th power. But 2 to the 7th power means that there are 7 2 multiplying to each other. The 5 of them can come out, right? Every for the fifth root, every 5 can come out as 1, right? So you're left, right, with 2 inside, 2 of the 2 inside. So 2 times 2 is 4, so that's why you end up with a 4 here. That makes sense. So you could do it this way, and then you can say, oh, that means fifth root of 2 times 2 times 2 times 2 times 2 times 2, 1, 2, 3, 4, 5, 6 times 2, right? And then so these 5 2's can break out the fifth root to become 2, and then you end up with what's inside left over is 2 times 2, so you end up with 2 times fifth power of 4. So you still end up with the same thing. You just logic them differently. Question? I mean, I'm taking the pain to kind of go through the details like this, just so that I want to make sure that you don't miss anything.
Okay, yeah, this is all, like, it makes sense. My main issue is, like, how the heck are we supposed to remember this whole process?
I don't know. You gotta do it. I don't have a good answer for you. There is no easy way around these. You literally just gotta go through this all the time, put in practice and practice problems, and then eventually it will become natural for you. So there's an automaticity in terms of your math doing, is that these are all logical, right? Because I know how to do this because in my mind I constantly connect to the logic in which these rules come about. So I don't simply just memorizing the rules, but I connect the rules with the logic that come before it. And I do it so many, I have so much of a practice and taking time to do this that it becomes second nature to me. You have to do that. There's no other way around it. You don't learn French just by teacher telling you the rules and then somehow you can do it. You have to practice, to the grammatical patterns and all that. Same thing with math. You can look at it in class and say, I get it. And then when test question comes and you're like, I don't remember it. Well, there's a gap in between, which you have to fill the gap, which is putting into the hard work. Okay, so now, just for the sake of practice, I'll give you these problems as a practice problem, sort of on the homework. I'll let Mr. Chen know that this is sort of as part of what you practice as homework.
Wait, do we have homework?
Yeah, I think so, because I don't want you to, after this today, and then go home and forget about what I said. So here, page 244 to 7, 8, 9, 10, 13, 15, and 16. Page 245, 18, 19, 29. And they may look a lot, but they're really tiny problems. They're like, just like what we did before. 31, 35, 37. That's it. When you get it done, take a picture of it, or whatever. Then you can email it to me. You can email it to me, and then I'll quickly grade them.
Can you post it on my record?
Huh?
Can you post it?
I will. Okay, so it's very simple. This is literally just section 5.1, and I have said what I just gave you actually gives you enough to understand 5.2. So the next big thing is just going back to function. Like you understand, algebra is all about functions. So we learn these patterns and rules or expressions and whatnot. It's all going to take us to functions. So 5.3 is radical function. We're going to talk about radical function. Okay? So it will lead us there. Any questions? Okay, I'm done for today. Thank you.
Yeah,